Let me start lecture 15, and the course is phase diagrams in single component and binary systems. And today we will talk on phase equilibria in single component system, and we will take H2 as a reference. So, till now what we have analyzed is basically condition of equilibrium, and that condition of equilibrium talks about the minimization of internal energy, maximization of entropy, minimization of Helmholtz free energy, which is termed as A, and minimization in Gibbs free energy, which is termed as G. And later on we have taken our discussion to only G, because most of our systems will deal with a constant pressure and temperature effect. So, we will be dealing with temperature and pressure effect. Okay. So, that is what we have taken everything in the form of Gibbs free energy. And we have also seen in case of a system where you do not have that condition of fixed composition, rather the composition can change if it is a closed system or if it is an open system where system can exchange matters with the surrounding. Of course, energy can also be exchanged. So, those cases we have to bring in one more factor in order to define a system apart from pressure and temperature, which is basically the composition, and the composition is taken in a smart way by considering number of moles of a system, moles of different components in a system, and in the way while analyzing that we come across one more parameter, which is chemical potential. And we have defined chemical potential is basically rate of change of Gibbs free energy of a system when 1 mole of substance of that particular component is added to the system without modifying the compositions of other components. So, that is what we have defined. So, now while doing that we have also derived 3 equations. Those 3 equations are basically Gibbs-Duhem equations, and we have said that these Gibbs-Duhem equations will be used in order to understand phase equilibria in a system where you can have multi-phase. It can be single component, it can be binary. Let us see how those equations can be used up in analyzing phase equilibria in a single component system to start with. So, now our topic, as you see, phase equilibria in single component, and we have taken H2O, which is a water system, and we will take also CO2 as another system, fine. So, now what we have done? We have seen that GPT, delta GPT equal to 0, or GPT goes to minimum. This is the condition of equilibrium. Okay. And now again, when you have taken composition into consideration, then we have seen delta G equal to V dP minus S dt plus summation of chemical potential of ith component. So, like this 1 to I. Okay. So, that is the equation we have derived, and this is one. Second equation what we have derived is basically Pt as a constant, put it in a summation mode, mu I n I. This is the second one, and the third one is n I d mu I equal to 0. This is the third equation, and we have defined mu I is equal to delta G dou G to n I P T, other components compositions are fixed. Now, if I take component to be 1, okay, system has only one component, then mu I, if I take this equation, n I equal to G. Okay. So, mu I equal to would be G by Ni, fine. So, this is nothing but molar free energy of that component. Okay. Now, interestingly, so that means these quantity are basically total free energy of the system. Okay. And here it comes molar free energy, when total free energy divided by number of mole of that particular component. So, that becomes molar free energy. This is applicable only in case of single component. Otherwise, this is molar, partial molar quantity, okay, a partial molar free energy. We have to now take a single component system and we have to find out the equilibrium condition. And before that, let us understand the physical significance of mu. What does it mean? In order to understand that, let us take few examples of other parameters. Let us say I have a system which is in a temperature T1 and then another system which is at T2, and let us say these are connected with a conductor, or let us say these two things are connected each other and the walls are diathermal. Okay. Then we will see that gradually this system will reach to a temperature which will be in between T1 and T2, and the condition is T1 to start with, T1 greater than T2. And how come it reaches to another temperature, which is the equilibrium temperature, new equilibrium temperature, okay, and that is thermal. And here, in order to reach equilibrium, so this heat will go from T1 to T2 body spontaneously. So, that means during the spontaneous process, it reaches another thermal equilibrium and heat would always be released by the body at a higher temperature. Okay. So, I can sense that if our body is at higher temperature, and connected to another body at lower temperature, so then heat will escape from body. Let us say this is body 1, this is body 2, body 1 to 2. Okay. So, I can sense that the temperature, in other way, temperature is a kind of indicating that it is an escaping tendency for the heat. Okay. So, higher temperature would always release it, or heat will be escaping from higher temperature to lower temperature. So, temperature is a kind of giving a sense that it indicates escaping tendency of heat. Similarly, pressure, so this is with respect to temperature. So, if I take pressure, let us say a body at a higher pressure and body at a lower pressure, P1 and P2, P1 greater than P2, if this is the situation. So, and this particular diaphragm, so what would happen? This pressure and this diaphragm is a kind of diaphragm which is not rigid, it can actually expand. So, you will see that this particular diaphragm will bend like this. Okay. So, that means the higher pressure would actually like to push the wall against a lower pressure. Okay. So, that means it also senses that expansion of a body is decided by the pressure difference, and higher pressure would always tries to expand. Okay. Or other way around, if you see, the molecules would actually like to go to a region with a lower pressure. Okay. So, that means it is also a kind of sense that, for example, if you have an ideal gas here and another ideal gas here at two different pressures. So, ideal gas at a higher pressure would always like to, those molecules always like to leave that high pressure zone to the low pressure zone, it will try to go there. So, this is also giving a sense of escaping tendency of molecules. Okay. So, it does not want to stay at a higher pressure zone, it will always tries to go to a low pressure zone. Okay. So, that means finally, if we release it, it will definitely reach to another pressure to attain mechanical till then that movement will continue, fine. So, it also gives a sense, the pressure is also giving a sense that escaping tendency or expanding tendency of molecules from high to low pressure zone, fine. So, that means I could see the temperature is an escaping tendency for heat, pressure is an escaping tendency for a molecule in order to achieve a similar pressure, mechanical equilibrium. In thermal case, it is a thermal equilibrium that any spontaneous process would like to go to a kind of new equilibrium condition. Now, let us look at the chemical potential. Okay. In order to understand chemical potential, let me consider a closed system, H2O liquid, H2O vapor, and this is at a particular temperature T. And if we have such situation, there would be an equilibrium pressure exerted by the vapor, which is a function of temperature. Okay. Now, if we have such situation, then let us say the temperature increases. It does not matter what is the quantity of liquid or quantity of vapor, it actually reaches that equilibrium vapor pressure. We also call it saturation vapor pressure. Fine. So, let us say this temperature increases. So, once temperature increases, we would see that the liquid, because higher temperature means higher vapor pressure it should exert. So, in order to increase the pressure, we need more molecules because it is a closed system, okay, and it is not expanding. So, that closed system has a constant volume. So, this is a constant volume. The system is a constant volume. So, that means in order to match the new equilibrium partial pressure or the equilibrium saturation vapor pressure, the liquid would convert to vapor. Okay. And if you hold there till it reaches to the saturation vapor pressure, the liquid will continue coming to, liquid atoms will continue coming to the vapor phase, okay, in order to achieve that saturation vapor pressure. So, in fact, you see that as we are talking about increase in temperature and that temperature we are fixing, okay, once the temperature is fixed, so then we see that liquid molecules have the higher tendency to go to the vapor phase. So, if we try to look at the chemical potential of liquid and chemical potential of vapor, I would see that this will be greater than this. Okay. So, if that is the situation, that then liquid will convert to vapor. Okay. So, that means you could see that, and here you could see that the partial pressure, the saturation vapor pressure, once it reaches there, it is an equilibrium, temperature is also equilibrium, okay, because we are fixing the temperature. So, now depending on whether this one would be high or this one would be low, which one would be high, which one would be low, depending on that, the molecule will leave the surface with a higher chemical potential. Okay. So, you can say that chemical potential indicating escaping tendency of molecules with higher chemical potential. Okay. So, the molecule would move from higher to low chemical potential. So, that means it is also indicative of escaping tendency. So, now let us say a situation, we have a sugar which is kept in a solution, sugar molecule, sugar cube, okay. This let us say sugar, and let us say this is at temperature T and pressure, fine. And so, let us say this is open system. Okay. Now, if we, and it will reach to a saturation point, and that is what we call it saturation, saturated solution and saturated liquid solution, fine. Now, if we increase the temperature, we reach to a new constant temperature and increasing it. So, then we would see that the chemical potential of sugar in sugar would be greater than chemical potential of sugar in solution, and then sugar will go from solid phase, this is a solid sugar, solid phase to the solution phase. Again I could see that it indicates a kind of escaping tendency of that particular substance with higher chemical potential in a phase compared to the chemical potential of that same substance in other phase in combination of it. Okay. So, let me just state this: substance will escape from a particular substance, a substance will escape from a phase with higher chemical potential to another phase with low chemical potential. Let us say the substance is I, and here log I, that I is basically the component, here also I is the component, two phases and same substance, and this is the I substance. So, if it is like this, the substance will leave, escape from a phase with a higher chemical potential to another phase with a low chemical potential of the same substance. And how long it will continue? It will continue till chemical potential of I in phase 1 equal to chemical potential of I in phase 2. Similarly, here also this will continue till it becomes equal. Okay. Fine. So, now in this way you can see that the content does not matter, okay. The how much quantity you have, the only thing matter is the chemical potential equality. Okay. Fine. So, you can also see that chemical potential in case of pressure, what we see, that escaping tendency or expanding tendency of molecules from high to low pressure zone. Okay. So, this is also indicating that the molecule should leave from a low chemical potential to high chemical potential. So, this can have a relation with the pressure, we can call it chemical pressure, and this particular movement will continue till del mu equal to with I equal to 0. And of course, when we do that, we consider T and P constant. So, this is equilibrium, and this equilibrium is setting up to considering the substance movement one into another, and this substance movement is somehow related to chemical potential, and that is what this is also termed as chemical equilibrium. Okay. So, it will the spontaneous movement will stop once that chemical equilibrium is established. Okay. So, now I could see that the physical significance of chemical potential, it is escaping tendency for the molecule to leave higher chemical potential surface to the lower chemical potential surface, right. So, now let us look at single component system. So, H2O, and H2O can exist for our consideration solid, liquid and vapor. These three phases it can coexist. Okay. It can coexist at a particular temperature pressure, we will come to that, but they can exist in case of water system. And let us consider that it is basically a closed system. So, we are considering closed system, and this is single component. Okay. So, if it is closed system single component, my general equation, chemical free energy equation is basically nothing but V dP minus S dt plus mu I dni. Okay. So, that is my generic equation, fine. But we will come to that. If it is single component, that means composition is fixed. I can actually ignore this term. Okay. So, this can be fine. So, let us not consider in the beginning like this. Let us consider that this particular situation, it is reaching at 0 degree Celsius and 1 atmosphere pressure. Let us consider that. Okay. And as per our this temperature and pressure, I would see an H2O would exist, and in fact, they will coexist at that temperature and pressure, and if it is a closed system, fine. So, when we have that, I can consider a generic equation, because since I am considering constant temperature and pressure, I will write G prime mu H2OS N H2S plus mu H2O liquid N H2O liquid. Okay. So, this is total free energy. Fine. Now, let us take this and this. So, this is in solid phase, this is in liquid phase, and I know that it is a single component. So, I can write G H2O should be equal to mu H2O or liquid. Okay. So, that means the molar free energy of H2O in solid as well as liquid, that will be same as chemical potential of solid and liquid, if since it is single component system, fine. Now, I can take it like this. Okay. I can write this, fine. So, if I write this, you see this term as per my Gibbs-Duhem equation, so which is this, should be 0. So, this term and this term, if we add them up, so they will if you add them, it should yield 0. So, I will be left with this term and this term. And at the same time, since it is a closed system, dN H2S should be equal to minus dN H2O liquid, okay, because it does not allow any mass transfer from one end to another, because with the surrounding, is a closed system. So, that is the situation. So, that means, if let us say there is a tiny amount of change of a solid H2O, which is ice, to a liquid H2O. So, this particular relation should hold, it will be same amount. So, I can take this one as, and if it is equilibrium, let us say if it is equilibrium, so it should be 0, then it should be mu H2OS okay. So, I know this relation holds for a closed system. So, then I can write mu H2OS minus, because these two are same amount, because the same amount would be if a tiny amount goes from solid to liquid. So, solid is leaving that tiny amount, the same amount will be accepted by the liquid. So, that means these two quantities will be same, and then this would become liquid. So, it becomes 0. So, I see okay, or I can write molar Gibbs free energy of solid should be equal to molar Gibbs free energy of liquid. So, this is equilibrium condition. Equilibrium. So, and this equilibrium is achieved at 0 degree Celsius and 1 atmosphere pressure. Okay, fine. So, that equilibrium is achieved. Now, when we have this, let us say the equilibrium is changed, pressure is not changed, it maintained at 1 atmosphere, this temperature let us say it goes 10 degree Celsius. Then I will see that solid water will go to liquid water, and we will see that Gs should be liquid water, Gs should be more than Gl. So, I will see that since it is solid going to liquid, so I have to calculate final minus initial. So, Gl is the final minus Gs is the initial. So, it should be negative. Okay. So, when that is negative, then definitely the system would do spontaneous work, and spontaneously liquid solid will convert to liquid, and vice versa happens. Solid water will come from liquid water if pressure remains at 1 atmosphere and temperature is less than 0 degree Celsius. That time it is basically solid coming from liquid, Gs should be less than Gl, and then I would see final phase is solid, Gs minus final phase minus liquid, it should be negative. Okay. Okay. So, that means it should be less than 0, less than 0. So, then spontaneously liquid will convert to solid. Okay. So, now though this spontaneity is basically a thermodynamic spontaneity, remember kinetically it does not happen straight. Okay. So, for example, liquid to solid transformation, it is not kinetically favored. Okay. So, that is what you need to go down a pretty high undercooling or low temperature to have the first solid to nuclei. Okay. So, that is a part of phase transformations, an actual happening of the phase transformation, actual solid to appear, but as per our thermodynamic consideration which will be governing the phase diagram. So, we should only consider whether thermodynamic spontaneity is there. So, these are all thermodynamic spontaneity. Thermodynamic spontaneous process. So, let me just stop here. We will take this particular topic in our subsequent lectures, and we will try to relate solid liquid, solid vapor and solid liquid vapor, and try to understand their phase equilibria, and we will see how to plot them on a plot consisting of y axis to be pressure and x axis to be temperature, and we will see that nicely we are able to combine all those three phases in a single graphical representation, which will tell us what temperature and what pressure we will have existence of single phase or two phase or three phase. Okay. So, that and all the existence will be decided by the equilibrium condition. Fine. So, let me stop here. We will continue our discussion in the subsequent lectures. Thank you.